Problem 517. So in this problem, we have two parallel plates, one with a plus sigma surface charge density, the other with a minus sigma surface charge density, i.e. we have a capacitor. And both of these plates are moving in a direction that is in their plane of motion, or another way, it's perpendicular to the normal direction of them. So the problem just has a generic two plates. So I'm going to make a description formalizing them. It's kind of what's pictured. I'm just going to make it very straightforward. Two plates. We are looking at them edge on. The top plate, from our perspective, has that positive sigma surface charge density, and the bottom plate has the negative sigma surface charge density. And both plates are moving to the right. The capacitor as a whole is moving to the right. Now, in example, let's see, 5.8 on page 235, we can see the magnetic field produced by a single plane of current. For that, we apply an Amperian loop that is basically a rectangle. One leg of the Amperian loop is entirely above the plate, one leg is entirely below the plate, and the remaining two legs cross through the plate. The enclosed charge, or the enclosed current, is equal to L times the surface current density. And so the magnetic field will be produced on the top and bottom legs of the rectangle. The side two legs are normal to the plate. By symmetry, there's no magnetic field among them. Using the right-hand rule, if the current is coming towards you above the plate, it produces magnetic field to the left, below magnetic field to the right. Furthermore, we can use the formula 5.22 on page 220, or 5.23 rather, on page 220, to see that the linear current density, K, is equal to the area charge density, sigma, times the speed, V, that the plate is moving. So combine this with the magnetic field equation 5.58 from an infinite plate. Each plate creates a magnetic field that has magnitude mu sub naught over 2 times sigma times V. Now direction. Again, the top plate is going to the right. So above it, the magnetic field is coming out of the page, and below it, the magnetic field is going into the page. For the bottom plate, the opposite is true. It's going to the right, but now it's negative, so we can use our left hand. Above that bottom plate, it's going into the page. Below the bottom plate, it's coming out of the page. If we are above both plates, out of the page above it and into the page above it. So if we're above both plates, those magnetic fields cancel. Same if we are below both plates, magnetic fields cancel. The only place where the magnetic fields do not cancel is in between the plates. In between the plates, it's below the top plate and above the bottom plate. Both are producing magnetic field into the page. So the magnetic field in between the plates is mu sub naught sigma V, and outside of the plates, it is 0. Part B asks, what is the magnetic force per unit area on the upper plate, including its direction? Now, we might be tempted to use this magnetic field, but we need to be careful, because this magnetic field is the magnetic field produced by both plates, and the top plate does not exert a magnetic force on itself. So we only use the magnetic field from the bottom plate. B is equal to mu sub naught over 2 times sigma times V. Now we can say that force, we can use this formula for magnetic force, QVB. Now Q, why don't we use the I version since we're talking about currents? You can do that, but I find this form to be a bit more straightforward. You have to do a little bit of hand waving with currents. FB is equal to QVB. So the Q, that's just the charge on a chunk of plate. So that is sigma times A. V, that is the speed of the plate. And B was this thing that we had just calculated, mu sub naught over 2 times sigma times V. We simplify them, we see that the sigmas and the V's both combine, become square, and we get this is the magnetic force. Now, as for direction, in between the, above the bottom plate, the top plate is above the bottom plate. Above the bottom plate, the plate is moving to the right, and it's negatively charged, so it creates a magnetic field into the page. Using right-hand rule again, motion is to the right, magnetic field is into the page, and we see that that creates a force upward. So the magnetic force is given by this formula right here, and it is directed upward. Now part C of this question asks, at what speed would the magnetic force balance the electric force? Well, we have the formula for magnetic force here. We can do something similar for electric force. Electric force is equal to Q times E, and once again, Q is sigma times A. Now, if we recall the electric field produced by a plane of charge, it was this formula right here, which means that the electric force is 1 over 2 epsilon naught times A times sigma squared. Now, because the two plates are oppositely charged, that is an attractive force, meaning it pulls the top plate downward. The magnetic field pushes the top plate upward, the bottom plate pulls the top plate downward, which means that if they are equal, then they cancel out. And so that's what we do next. This is the electric force, this is the magnetic force, and we see already that it doesn't matter the area, and it doesn't even matter the charge density. Those terms will cancel when we're trying to say when are these two forces equal. And this kind of makes sense because both, when we were talking about when do electric force and magnetic force cancel on a particle, we found that the charge likewise didn't matter because both were linearly proportional to the charge. All that's left is this 1 over 2 epsilon naught here and mu sub naught over 2 times v squared here. So let's move the 2 over mu sub naught to the, or mu sub naught over 2 to the other side by turning it into mu sub naught over 2. The 2's cancel, and we're left with 1 over epsilon naught mu naught is equal to v squared, or v is equal to the square root of 1 over mu sub naught epsilon naught. Now you might recall from when, I'm not sure if we actually talked about this, but this term right here, 1 over the square root of mu naught epsilon naught, that is the speed of light. In order for these two plates to not experience any net force, they would have to be moving at the speed of light.